Hello everyone, welcome to chapter number 3. In this chapter is about series solution of second order differential equation, and this is another method to solve second ODE, and the solution is we're gonna get in terms of series solution. In the last chapter we already talked about second ODE. That chapter we solve second order in terms of like the determine coefficient method, and this chapter is another method to solve the second ODE. Okay, in this chapter we will focus only on linear differential equation of second order. Normally when we have second order ODE, we're gonna have something like this, right, in the linear form. Okay, and the general form is px times d square y over dx square plus qx times dy over dx plus rx times y equal to 0. When equal to 0 is the linear form of second order. Okay, in this form we can rearrange to get equation 1, which is d square y over dx square plus qx over px times dy over dx plus rx over px times y equal to 0. And after we rearrange the second ODE into this form, we can use a power series to represent equation 1. To do that, we have to get a point first, which we call like x0s. X0s, there are two kinds of x0s. The first one is ordinary point, and the second one is singular point. And after that, we can solve to get the series solutions by using these 2 points. Okay, and in each point we use different methods to solve the solution. Okay, we're gonna talk one by one. Okay, to solve the solutions of second ODE using ordinary point, first you have to know what is the ordinary point first. Okay, let's take a look at this. The ordinary point is at any point that's called xs that satisfies pss is not equal to 0. If pss equal to 0, it's gonna be singular point. Okay, let's take a look at this example 1. We have d square y over dx square plus x dy over dx plus x square plus 2 times y equal to 0. This is linear differential equation of a second order. Okay? And in this form, it's already rearranged in terms of equation 1 from the previous slide. So PS in this equation is 1, right? X over 1 here. So the PS form, the PS term is equal to 1. So that means every point is ordinary point and no singular point in this case. Okay, because there no any term, this PS term, that is equal to 0. Okay, and take a look at second example. We have x minus 2 times dy d square y over dx square plus x dy over dx plus 1 over x times y equal to 0. This is also linear second order. Okay, but here we have PS, which is x minus 2, so we have to rearrange into this form first. We're gonna get d square y over dx square plus x over x minus 2 times dy over dx plus 1 over x times y over x minus 2 equal to 0. Okay, this is the equation number 1. That's the form of equation number 1. When we look at this is the PS function, which is x minus 2. So in this case, when x equal to 0 or 2, we cannot find the solution here, right? Because it's x over like zeros, that, that means we cannot find the solution. So whenever we have something like this, is this number like 0 and 2 is a singular point. Okay, it can be any other numbers, right? It depends on this PS function. So in this case, it's 0 and 2 is a singular point, and the other points are the ordinary point. Okay, so in this case, you have to know what is the ordinary point, and you have to know what is singular point. Okay. For the solution of the second order in terms of series solution, we can write the answer in terms of this form, which is y equal to c0 plus c1 times x minus x0. x0 is the point that we define, plus c2 times x minus x0 square plus blah 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 until cn times x minus x0 x to the n plus blah blah blah. Or we can write in terms of summation form, which is the summation of cn times x minus x0 power n from n equal to 0 to infinity. Okay, and c0, c1, c2, and cn is just a constant, and we also have to find these constants. Okay, and to get the solution in this form, we have to follow the step, which is I'm going to show you an example. And in the first one, I'm going to show you to find the series solution using the ordinary point, which is the easier one than the singular point. Okay. Okay, now let's take a look at example of second ODE by using series solutions near ordinary point. Here we have x squared minus 1 times dy squared over dx squared plus 3x times dy over dx plus xy equal to 0. And we also have initial condition, which is when x equal to 0, y equal to 4, and when x equal to 0, y power equal to 6. Okay, this is the problem that we have, second ODE. So in the first step, you can rearrange this form into the form equation 1 from the previous slide, or you just take a look at this PS function. This is PS, QS, and RS, right? PS is x squared minus 1. So when you consider this, you have to think what is it that makes this term go to 0, which is x equal to plus 1 and minus 1, right? So when x equal to plus 1 and minus 1, these terms go to 0. So this is the value that make this term going to be the singular point. So in other numbers like 0, 2, 3, 4, 5, or whatever, they are ordinary points. So I said it here. All values of x is ordinary points except x equal to plus 1 plus minus 1. Okay. So in the first step, what you do here, you just take the general form of the solution, which is y equal to summation of cn times x minus x0. Don't forget x0 here. Power n. Okay, from n equal to 0 to infinity. And you have to make exception, which is x must not be equal to plus 1 or minus 1, which is x0 not equal to plus minus 1 here. So what you do next is you do the first derivative and second derivative, okay, of the general solution here. But since x0 here is we have initial condition, which is x0 equal to 0, so you substitute x0 with 0, so you're gonna get x, just x only. So in the general form, it's gonna be y equal to summation of cn x power n from n equal to 0 to infinity. And the first derivative of this one, the equation 2, you're gonna get n cn x power n minus 1. And when you do the first derivative, n here is gonna be starting from 1, right, and to infinity. Again, when you do the second derivative of this y term, or do another derivative of this form, then you're gonna get y double prime equal to the summation of n times n minus 1 from here times cn x power n minus 2. Okay, then what you do next is you substitute y here, y double prime, y prime and y double prime into the problem here, which is in this form. Now go to the next slide. So here you substitute the general solution of y prime and y double prime into the problem, and you get this form, right? Then you multiply x squared minus 1 into here, or 3x into here, and x into this summation form. Okay, and then you're gonna get this form, which is when you multiply x squared into here, you're gonna get x to the n, right? X to the n here in this form, and the minus sign, which is in this form, you get minus and keep the same form here, plus 3x, you have x here, so x times x to the n minus 1, we get x to the n. Okay, and x here, you get x to the n plus 1. The next step is you adjust x to the n. Whatever you can choose any number, like you can adjust to the x to the n, or x to the n minus 2, or x to the n minus 1. It doesn't matter. Just pick one. Okay, here I choose x to the n plus 1. So from here, in the first term, it's the same. Just take it down. And in the second term, which is this one, so when you adjust x to the n, which is you have to plus 2, right? Here you have to plus 2 in x to in this form to here. So whenever n, you see n, it's gonna be n plus 2, and this is n minus 1 plus 2, so you get n plus 1. Okay, just follow carefully. Okay, and here cn, so we're gonna get cn plus 2 too. Okay, so these terms of here, when you see n, you have to plus 2. This is plus 2, this is plus 2, this is also plus 2. Okay, but here from the summation form, this is n starting from 2, but when you add 2 here, from here you have to subtract 2 or minus 2. So n equal to 2 minus 2. So you get n equal to 0. So this one is going to be n starting from 0 to infinity of this form. And then in the next step, this is n to the x to the n. So take it down, the same. And in this step, this is you have to minus 1, right? So it's going to be cn minus 1 here, and x to the n. But in this case, when you add when you minus 1 in this summation form, is you have to plus 1. It's the opposite. This is minus, so this is plus, Again, this one is u plus and this one is minus. If it go the opposite, just remember this. So this is going to be n starting from 1 to infinity and equal to 0. Okay, after you adjust every term to x to the n, now you look at the summation form, which is the starting point of n of each term. From the previous slide, you see that n starting from 2 and from 0s and from 1 and from 1. Just look at the previous slide, okay? In the next step, you look at the highest value of the summation form, which is n equal to 2. So then every term here in the problem, you adjust every term to n equal to 2 by substituting with like 0 or 1 or like whatever number until n equal to 2. Okay, in this case we substitute with 0 and 1. Okay, in the first term it's the same because n equal to 2 already, just take it down here. In the second term, n starting from 0, so in the first step you substitute n equal to 0 here, right? Go back to the previous slide, and then you get 2 times c2, and also substitute with n equal to 1. You get 3 times 2 times c3 times x. Okay, and then when n equal to 2, you just write down here. And in the third term, okay, n starting from 1, so you substitute just 1 only. Substitute with 1, you get c1 times cx, c1 times x. Okay, and when equal to 2, you just write down here plus, and the fourth term is n equal to 1, so just substitute with n equal to 1 to get c0 times x plus this term. So now we have the same summation form, which is summation of n equal to 2 from n equal to 2 to infinity for every second term. Okay, and also x to the n every term. So in the next step, you just combine all the summation form together, you know, and just look at the Cn. Okay, this is Cn plus 2, starting from the highest one first. Cn plus 2, we have this one, which is n plus 2 times n plus 1. Okay, and the minus sign here, don't forget. Okay, and in the second term, okay, we have Cn plus 2, we have Cn here, and Cn minus 1. So this is also Cn, this the same Cn. So n times n minus 1 plus n, okay, or plus 3n. There's 3 here too. So n times n minus 1 plus 3n, and you can combine, you get n times n plus 2 in this one. And in the last term, it's Cn minus 1 here, that's only 1. So it's Cn minus 1 times 1 altogether here times x to the n. Okay, and for the term that without the summation form, you write down starting from the lowest first. This is minus 2 c2, there's no x here. Okay, and the second term is c0 minus 6c3 plus 3c1 times x. This all combine x all together. That's this term, right? And also this one. Okay, and next you solve to get the solution. Okay, look at this one first. This one you just take it equal to 0, and this one equal to 0. Okay, so in the first term, minus 2c2 equal to 0, then c2 equal to 0. Okay, you get c2 equal to 0. And this one is c0 minus 6c3 plus 3c1. Okay, and just take it equal to 0, and then you rearrange to get it this form, which is c3 equal to 1 over 6 c0 plus 1 over 2 c1. Okay, next, in the next step, you just look at the form with the summation form, and consider inside this form you will see that we have minus n plus 2 times n plus 1 cn plus 2 plus n times n plus 2 cn plus cn minus 1 and equal to 0. So take this term equal to 0, okay, without the x to the n and the summation form. And in this case, n has to start from to be started from 2, okay, because we use the summation from 2 in the previous slide. And then in this one, you just rearrange, take the highest value, which is n plus 2, to the left hand side, and the rest go to the right hand side. Okay, and this is we call recurrent relation. Okay, and n here is starting from 2. So then if we substitute n equal to 2, we're gonna get c4 equal to 1 over 12 times c1. And when we substitute n equal to 3, we get c5 equal to 1 over 8 c0 plus 3 over 8 c1, and blah blah blah. If we substitute like 3, 4, 5, 6, whatever. So now we know what is the value of c0, c1, c2, c3, c4, c5 until infinity. But in this case, we just show you like we get c0, c1, and c2. That's more than enough. Then you substitute c1, c2, c3, whatever into the general form of the solution. Okay, which is c0. Just go back to the previous slide and look at the general form, and just plug in the value of this. So we're gonna get c0 plus c1 x plus, because c2 equals to 0, so we don't need to substitute c2, and this is c3, and c4 is here, 1 over 12 c1. Actually this is c1. Okay. This is c1, and plus c5 is this form, and you can just stop here to get the general solution form, or you can further reduce in terms of like the more looks nicer one. Okay, in this case I will show you like we can reduce this form into c0 form plus c1 blah blah blah. But this one is getting more difficult, so you just don't think about it. Just take this form. Okay, since we have the initial value problem, so then we have to find the value of c0 and c1. Okay, from the general solution that we got in the previous slide, then you have to plug in this initial condition, which is when x equal to 0, y equal to 4. Okay, so you just plug it in when x equal to 0 in the previous slide and y equal to 4. Then you see that you get c0 equal to 4. Okay, so that means c0 is here equal to 4. But we also have the first derivative, which is the first derivative is here. When x equal to 0, the first derivative equal to 6. So when you do the first derivative of the general solution of y, you get this form, right? Then you just plug in x equal to 0 here, x equal to 0, so this all of this go to 0, and this one all go to 0 except 1 here. So that means here y prime equal to 6, right? So that means c1 equal to 6. We already got it, c1 here. So c1 equal to 6. So in the final solution, you have to plug in the value of c0 and c1, which is 4 and 6. So the general solution or the final solution is going to be y equal to 4 times, in this parenthesis, plus 6 times this parenthesis plus blah blah blah. Here is the solution in terms of series solution of the second order that we solve. And this method we're using ordinary point, which is easier one compared to the singular one. Okay, and in the next video, I'm going to talk about the series solution in terms of the singular point. Okay, I'll see you in the next video. Okay, bye.